Greetings, students. Mr. Harrison here from school. Got a PowerPoint for you on energy forms and also energy changes. We have another unit coming up on the actual energy conversions, but this is kind of our first step to that. So let's dive right in. Energy can be detected through our observative senses. So observation is the five senses: seeing, tasting, touching, smelling, and hearing. So you can hear it as sound, you can see it as light, and you can feel it as wind, but either way, energy is all around you. So what is energy? Let's find out. Energy can be defined as the ability to do work. So a lot of people, if I ask you, what does energy look like? People describe things like something that's hot or something that is moving really fast or going crazy is a phrase a lot of people use. But the bottom line is all of those definitions leave out something. Because you know that if you we're going to keep going back to this bow and arrow idea. But if you have a bow with an arrow in it and you draw the bow, you pull on the string, there's energy in that system, but it's still not moving until you release it. So how do we have a definition of energy that includes that idea that of the energy that is about to be released, but it's still there, it's just not moving yet? And yes, this does relate to something you've learned in the past, if you're wondering, but we added this phrase, the ability to. If energy was just work, that would include all that movement stuff, because work takes motion, right? And we'll talk about that in a minute. But energy is also the ability to do the work. So it could move at any moment is kind of the main idea. So work involves force. If you push or pull against an object, that's called force. And if you push or pull with enough force and it moves the object in the direction of the force, then you've done what's mathematically termed work. So if an organism or object does work, that means it's exerting a force over a distance to move an object. And that means the object or organism is using energy as well to do that. And since work and energy are so directly connected, we actually use the same units to measure work as we do to measure energy. It's called a joule. Capital J is the abbreviation. But work and energy use the same unit because they're that connected. So objects can use energy to do work. That's the traditional idea. But objects can also gain energy because work is being done on them. So that bow and arrow idea, as I do work on the string of the bow, that bow and the bow and the arrow as a whole combination of devices is gaining energy because I'm pulling the string back. So I'm doing work on the bow, but the work is being done on the bow, and from the bow's perspective, it's gaining energy. Then you've got the idea that both of these terms that you've heard before, kinetic energy and potential energy, if you add them up, that's what this word the word sum right here comes from addition as a math function. If you add the potential and the kinetic together, you get the total amount of energy in a system, and that's called mechanical energy. Now, later on, we're going to define mechanical energy as useful motion in the next unit, but for now, mechanical energy is just the sum of kinetic and potential energy because it has to be the total amount of energy. And we'll explain how they work together here before we're done. All right, so real quick review. Kinetic energy is movement or motion. Potential energy is the energy that's stored, and it implies that it's not moving. Now, something with potential energy can be moving, but the actual motion energy is kinetic, and the energy that's not moving yet is potential. Kinetic energy is the energy of motion or movement. Because it's associated with motion or movement, it makes sense. It's very intuitive to think about it this way, that the faster an object moving, the more kinetic energy it has. Like if I throw a baseball at 30 miles per hour, it's going to have less kinetic energy than if I throw it at 80 miles per hour. It just makes sense. But also, the mass has something to do with it. The greater the mass of a moving object, the more kinetic energy it has as well. That's the idea. If I throw, I like to think about kinetic energy in terms of if something that was moving contacted something, how much damage would it do to that other object? That's how I remember the math, I guess, of kinetic energy. But if I take a baseball and throw it 30 miles per hour at a brick wall, and then I take a bowling ball and throw it 30 miles per hour, the same speed, at a brick wall, obviously the bowling ball is going to do more damage because the more mass you have, the more kinetic energy you have. Because kinetic energy depends on both mass and velocity. Here's the equation for kinetic energy. It's KE, kinetic energy, equals mass times velocity squared, all divided by 2. Mass times velocity squared divided by 2. All right, now, in a second, I'm going to have you pause the screen. I want you to think of an answer for this. What has a greater effect on kinetic energy, mass or velocity, and why? What has a greater effect on kinetic energy, mass or velocity, and why? And look at the equation to help you. So now I'm going to have you answer that in your head and come back. I'm going to have you pause it and don't unpause it until you have an answer in your head. So go ahead and pause your screen. All right, welcome back. Hopefully you've got an answer in your head to the question, what has a greater effect on kinetic energy, mass or velocity? Let me explain what the answer is. Never mind this for a second. That's just the kinetic energy. Here's how you calculate it. Mass times velocity squared divided by 2. Both of them are equal because in terms of the fact that they're both on the numerator side of the fraction, but velocity gets multiplied times itself. So velocity has a far greater effect on mass or on kinetic energy than mass does because the velocity gets squared and the mass does not. All right, potential energy. That's the stored version. It's not moving yet. Excuse me. It can be stored in a variety of ways. Number one, chemically in fuel or food, or possibly in the nucleus of an atom. In all three of those, it's not actually moving, but it could be at any point. It's stored inside of those things. And kinetic energy could be stored because of the work done to it or done on the object. For instance, when you stretch a rubber band, you're adding potential energy to the rubber band. When you wind a watch, when you pull back on a bow's string and arrow, when you lift a brick high in the air, all of those 4 things are doing work on an object and storing energy because of the work done on that object. All right, first type of potential energy. So like if you think of energy as like there's 2 types, kinetic and potential, both of which make up mechanical energy. Now we're diving underneath potential and kinetic and giving examples of different types of potential and kinetic. The first is a type of potential energy called elastic potential energy. That's energy that's stored due to being stretched or compressed. So if you stretch a rubber band, you're storing energy through elastic potential energy. If you compress a spring, like in this Jack in the Box, you push it down. That's why it jumps out and scares you, because you're storing potential energy when you compress the string. It's the same principle, but kind of in reverse. Instead of stretching, you're compressing. Then you've got gravitational potential energy, which will be abbreviated GPE, gravitational potential energy. And the best example would be like a waterfall, but a lot of things have it. And potential energy that's gravitational depends on height. Because if someone gave you the choice, if you're being punished, you had to either stand underneath a 5-foot waterfall or a 50-foot waterfall, it would be much less pleasant, much more uncomfortable to stand under the 50-foot waterfall than the 5-foot waterfall if it had the same amount of water going over. And that's because the higher something is, the more gravitational potential energy it has. Therefore, the more energy as kinetic energy that it can release once it's converted. So the higher something is, the more GPE it has. So things like the waterfall, like we said, a suspension bridge, falling snowflake, me standing on top of a desk, all of those examples, the object would have gravitational potential energy. Or simply put, if it's not standing or laying on the ground, it has gravitational potential energy because it could fall to the ground. It has potential to fall. And the higher up you are, the more GPE you have. So you've obviously, I'm assuming, heard the phrase, the bigger they are, the harder they fall. Well, it's not just a saying, it's actually true, mathematically true. Objects with more mass have a greater gravitational potential energy. As a matter of fact, the formula to find it is weight times height, or mass times height. So in the same scenario, but in reverse, we're not really doing this, don't worry, but if there's like bullies and you had no way out and they would let you go after they kind of hazed you a little bit, and they said, all right, you get the choice. We're going to hold some type of like object on top of a foot above your face, and we're going to drop it on your face. And you can choose which object. And they give you a choice between a golf ball and a bowling ball. You'd be very foolish to choose the golf ball because it just makes sense that the bowling ball is going to hurt way more. Probably do some serious damage, even at a foot. And that's because the bowling ball has a greater mass. Even though their height is equal, the mass of the bowling ball is much bigger than the mass of the golf ball. So it does more damage because it has more gravitational potential energy. All right, now the classic example of the kinetic potential energy conversion in our favorite theme park ride, the roller coaster. Now think about when you start a roller coaster. The very first step to the roller coaster is one of two things. Either you do all the work and you climb up the stairs as you wait in the line to start the roller coaster, and the roller coaster starts way high up in the air at the highest point, and that gravity powers the rest of the ride. Or you climb like halfway up, and then the roller coaster immediately, once you get like belted in, the roller coaster immediately starts carrying you to a higher point. That tick, 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 and you see the edge of the hill coming, and you're like, oh, I immediately regret this decision. And then you get to the top, and then it's all the fun and screaming and all that. But first you got to somehow, either through your steps, getting up the steps, or from the ride itself, you got to get carried to the highest point. So then after you're at the highest point, you have the maximum amount of potential energy, because remember, potential energy from gravity depends on height. From that point on, it's just a trade-off between potential and kinetic, and then back to potential, and then back to kinetic, and back to potential, depending on if you're going up or down a hill throughout the rest of the ride. So take a look at this. First time, just watch the car going down. It's going downhill, picking up speed. Then it goes through, Then it goes through a loop. Then it's going back downhill, picking up speed, slows down to go up the loop, speeds up on the other side, slows down going up the hill, speeds up on the other side, slows down, then speeds up. Now this time watch kinetic energy, KE, and potential energy. Kinetic energy is at a minimum, but it increases as you go down the hill, and potential energy decreases at the same time. Then the same process reverses itself, going up this hill, goes back down, up the hill, back down. Look what's happening to kinetic and potential energy. Notice they move in sync with one another. They're trading one for the other. Kinetic for potential, potential for kinetic. Now watch as kinetic and potential energy go up and down. Watch what happens to total mechanical energy. As you can see, as kinetic energy and potential energy are traded for one another, total mechanical energy remains unchanged. That's because, remember, total mechanical energy is a sum of kinetic plus potential. Now I'll let you watch it one more time and observe whatever you want to see. But as you're doing that, let me tell you that this is not a realistic roller coaster. This is a frictionless roller coaster, because in reality, some of that energy in the conversion between kinetic and potential, or potential and kinetic, would be lost due to friction and or sound energy. In this one, obviously, it's not. So really, in a real roller coaster, mechanical energy would slowly go down and down and down a little bit each second. All right. Now, thermal energy. This is a type of kinetic energy. It's also known as heat. You probably already know that. But did you know that heat is caused by the motion of atoms? The faster they are, the hotter they are. Think about water. If you take an ice cube, very little motion that you can see with the naked eye. As it melts and becomes a liquid, there's a little more motion. It can slosh around in the pan. As you take that liquid and you start to turn it into water vapor, so it's turning into a gas through evaporation or boiling, you can visibly see that there's much more motion as it gets hotter and hotter. And that's because thermal energy is a kinetic energy. And this is another tricky little distinction here. Thermal energy is not actually temperature, but it can cause changes in temperature. But the reason it's not just temperature is because thermal energy can also cause a phase change. Remember when we did the phase change graphs earlier? Thermal energy can be added at a constant rate, but sometimes the temperature doesn't continue to go up. It flat lines. It stays the same for a time. So if you take ice and you heat it up through adding thermal energy, that ice is going to raise in temperature and get higher temperature, higher temperature, higher temperature until it starts to melt and turn into liquid water. And during the melting phase change, the temperature stays the same the whole time until every last chunk of ice is melted. Then once it's all melted and it's all liquid, that liquid water is heated up, increases in temperature, and increases and increases and increases in temperature until you get to the next phase change, which is at about 100 degrees Celsius, and that is evaporation or boiling. And while the water is turning into a gas in evaporation or boiling, temperature stays the same because all that thermal energy, even though it's being added the whole time, is being used to do the phase change. But either way, it's a type of kinetic energy. Then you got chemical energy. Remember how we talked about atoms bond together to form compounds? Well, those bonds in the atoms often store energy. And when you break the bonds, energy is released. We talked about exothermic reactions that get hotter. They get hotter because there's energy released from the bonds. So technically, chemical energy is a stored energy because while it's chemical energy, it's not being released. But once we start releasing it, a lot of the times it's given off as thermal energy. So think of an exothermic reaction. If it's just sitting in the compound, it's stored in those bonds. But once we start to break those bonds, it's released as thermal energy. So that way it's converted to kinetic energy. And as we said before, fuel and food are the classic forms of stored chemical energy. Fuel and food. A lot of people don't realize that when the reason we eat isn't so we can get fat or so we can think things that taste good or taste things that we think are good. It's because we need energy. And the bonds of the compounds in our food are the things that give us the energy that our body can use. Same thing with fuel, except for instead of our body, it's in a car or something like that. All right, now we got electrical energy. Electrical energy is all about moving electrons. It's the flow of electrons. It's literally the definition of electricity, the flow of electrons. So since electricity has to be flowing, it's got to be kinetic energy because it's movement of electrons. And then, of course, the power lines carry that electrical energy into your home. You plug things into the outlets and you get power. Next type is radiant energy. Radiant is from the electromagnetic spectrum, which includes visible light. It also includes infrared light, which is the type that we know as like heat. This is like the magical type of heat because it can actually heat things up without touching, like through the air. Electromagnetic energy also includes X-rays, radio waves, laser light, and a lot of other things. It's very, very cool. That's actually in our next unit, but this is just one of the types of energy. It's called radiant. It's kind of like that heat transfer without touching. And then this is kind of review from what we did before, but nuclear energy is another form of stored potential energy. In the strong force that holds the nucleus together, there's a stored energy. Therefore, it's potential. And if we do things like fission and fusion, fission is splitting of one nucleus into two. Fusion is two nuclei fusing, colliding, joining into one. Both of these processes release tons of thermal and electromagnetic energy. So as it's stored, nuclear energy by the definition of itself is a stored energy, a potential energy, because it's not being released. But once we do fission and fusion, now we're releasing that stored nuclear energy, and it's converting it to kinetic energy in the form of electromagnetic or thermal. And then again, we've already talked about this, but the sun is a fusion reactor. It does that where two hydrogen atoms, two hydrogen nuclei join and fuse and collide and form one helium nucleus. And that process is releasing the stored nuclear energy in the hydrogen atoms. So it's potential energy, but when it's actually burning, the sun is converting that potential nuclear energy into kinetic fusion thermal energy. And since we live pretty close to power plants, I know there's one for sure in Lake Anna. I think there's another one closer, but it converts nuclear energy into electromagnetic energy and then also thermal energy. And that electromagnetic and thermal energy is what turns the turbine, which does electromagnetic induction, converting that motion into movement of electrons, which is called electricity, and that pumps to your homes. And as far as we know in the universe, nuclear energy is the most concentrated form of energy. That's why the stars use nuclear fusion. All right, let's talk about kinetic potential energy conversions in another light, and that is shooting a basketball or throwing a basketball in the air. So as you shoot a free throw, say, you're going to shoot the ball up in the air, and then it's going to fall back down. There's tons of energy conversions that take place. So let's take a look. Here's where you release the ball. This is obviously exaggerated because it's going really high, but each phase here, as it moves towards its peak, you are injecting kinetic energy, which is moving the ball against the force of gravity, therefore converting the kinetic energy that you put into the ball, slowing it down, and converting it to maximum potential energy at the peak. Then as it starts to fall, that potential energy that was built up when you shot the basketball, is starting to get converted back into kinetic energy on the way down. So this is maximum potential energy. Down here would be minimum potential energy and maximum kinetic, because it trades for kinetic. Potential and kinetic purely trade for one another, like one-for-one trade. The last thing is the law of conservation of energy. This is something from an earlier unit, but it states that energy can be neither created nor destroyed by ordinary means. Or you could say energy can't be created or destroyed. However, and this is the big catch of this unit, it can be converted from one form to another. So you never lose any of that energy, and you can't get it from nothing. And if it appears that you lost it or you got it from nothing, scientists look for it, and that's led to many tremendous discoveries, both in terms of just pure scientific value and technological advancement. A lot of those things have come from looking for the energy that looks to have disappeared or looks to have come from nothing. All right, go ahead and close this video down and get started on the questions.